So we know that health is a continuum. It's not simply absence of disease, but the current healthcare system is focused really at the disease end of that spectrum. In fact, 97% of healthcare resources are directed toward treating disease. And we know this is a problem because other behavioral determinants, lifestyle determinants of health are really far more important when it comes to understanding our health. So in fact, behavioral patterns account for 40% of premature deaths. That's more than genetics, more than social circumstances, environmental exposures, or even more than healthcare itself. So I'd argue that we're doing a very good job here at the genetic end of the spectrum. We're doing biomolecular profiling. We're understanding how our genes contribute to our function and our behavior. But in order to make that data actionable, we have to do an equally good job at the other end of the spectrum, understanding our outcomes, how we feel, how we function, and ultimately how we survive in the real world. And we need to do a better job measuring how lifestyle and behavior contribute to all of this. Another interesting factoid: it takes on average 17 years for new biomedical innovations to go from idea to clinical practice. We know that's far too long. We were talking this morning about race cars, the automotive industry in general, how it translates data into action. Today's data gets translated in tomorrow's vehicle designs. So we could really be doing a lot better improving that innovation cycle in healthcare. So that was the little introduction. I want to spend the rest of my time talking about a clinic that I've been building at Mount Sinai so that we can do a better job of leveraging data and technology to redesign how we both measure health and ultimately how we deliver healthcare. So this is our prototype clinic. This is not a render. This is a real space. And what you're essentially looking at is a white box that's literally air-gapped from the rest of the hospital, from the rest of the Sinai Health System. And the reason we built this as an isolated standalone is so that we could prototype very rapidly how we might integrate new technologies, new ways of capturing data, and deploy those into the healthcare system. So a little bit about how we do this. So we invite patients to sign up online. They input their essential medical data, their health history, how they sleep, their nutrition, their physical performance, and their mental health, and then they schedule a visit with us. On the day of their visit, they come to our space and they spend about an hour with us going through a variety of health assessments, starting with the very traditional vital signs, blood draw for clinical labs. But we're also doing a little bit more with that as well. We do a 3D body surface scan for anthropometrics. We do body composition testing. And then we assess our patients' cognition, gait, strength, dexterity, and a bunch of other measures. We're also taking the opportunity to do research on the back end. All of our patients are asked to give consent for research, and if they do, that blood sample also goes to our biobank, where DNA gets extracted and gets used for our in-batch genetic testing on a research basis. At the end of that hour visit, we have a conversation with the patient. All of their data is synthesized together on screen, and it's not that we're going through each and every data element in detail. It's really so that we can have a human interaction, doctor and patient sitting together, and we use the data to guide the conversation so that the patient can understand how all of their health data relates and what they can do to optimize their own health, improve their own quality of life. Ultimately, the goal is to come up with a very concrete and actionable plan so that the patient can leave our clinic, take that data back to whoever they trust with their health. It could be their primary care doctor, it could be a nutritionist or a therapist or another family member. But the important thing is that the patient has access to their own data and they can use their own data to track their progress as they improve their own health. So these are our clinic objectives in a nutshell. First and foremost, we're empowering patients with a comprehensive health assessment, what I believe is the most comprehensive health assessment currently available. But that's not the only stakeholder in this. It is the most important one, but we have 3 other stakeholders as well. Hopefully, we're unburdening providers. Physicians in the room and other providers know that we're spending far too much time working on data collection. Our heads are buried in screens. We're taking notes on what our patients tell us, and only then at the end of the visit do we have just a brief moment to tell our patients to eat less, exercise more, and quit smoking. Our third stakeholder, researchers. So we are a research institute at Mount Sinai. We started as a group of data scientists that are very used to sitting downstream from where the data is collected. And traditionally, we're harvesting data from the electronic health record or from our genetics repository. But we know that when it comes to understanding health, that data is pretty limited, right? We have, in most cases, if you're healthy, you might have a healthy pregnancy or perhaps that penicillin prescription in your electronic health record. In order to do a better job of leveraging all that data, making it useful, we need to capture a much broader array of data from molecules up through population health and longitudinally across time. And our last stakeholder group, and what's most exciting to me about all this, is innovators or product developers. Traditionally, product development in healthcare is very far removed from where the patient and the provider is. And if any of you who work in product development know, it's all about understanding your end user. So by putting everyone together physically in one environment, we're getting a better sense of what actual patient problems and provider problems are. We're able to develop prototype solutions to those problems, deploy those solutions in the clinic environment, see what works, see what doesn't, and iterate on that. So let me explain this another way. This is the existing healthcare system. No joke, this is a slide I downloaded from the government website. And all these stakeholders that I've mentioned, patient, provider, researcher, and innovator, we're very separated. We're very siloed from one another. So what we're hoping to do is bring everyone together under one umbrella. The patient and provider enters into a care cycle, and that's how we deliver better health to our patients. But we're also using that data and the insights that we collect to deliver to our researchers and innovators and enabling new discoveries and new product developments. And then, of course, we're closing that feedback loop. And this is the most critical aspect of what we're doing. It's not enough to develop new solutions and deploy them. We have to feed them immediately back into that care cycle in order to know what works and what doesn't. So importantly, the clinic that we've built is one iteration on this, but as we all know, the future of healthcare is not brick and mortar. The future of healthcare is out in the real world where we all function and go about our daily business. So we're looking at other models, other care cycles, starting with our pop-up clinic, but also looking at a kiosk, a smaller, scaled-down version of what we've built, an app, and even a network of different models. So the clinic is the means, it's not the end. So I'm going to leave the last minute. Hopefully we can have a discussion at the end of this, but I just want to leave you with 5 prescriptions for success. First off, we know health is a continuum. It's not just an absence of disease. And I argue that precise measurement of outcomes, not just biomolecular profiling, is essential and necessary. And research must encompass implementation and delivery. Yes, papers are important for us to do our work and for others to build on our work, but those are a means. Those are not the end. We have to borrow from startup methodologies. We need to decrease that product development timeline so that we can more quickly identify what works and what doesn't. And lastly, I like to say we're innovating from the outside in, meaning we're starting with health and progressing toward disease. This is a pragmatic way of getting things done and getting things done as quickly as possible. So with that, I'll thank you, and I'll look forward to your questions later.
Hello? Okay, great. So good afternoon, everyone. Thank you so much for coming and to Dr. Chang for inviting me to speak today. And I'm going to talk about reinforcement learning. And in the second half of my 10 minutes, I will be talking a little bit about how data movement is actually important to many applications. It's an aspect that hasn't yet been explored too much during this meeting, so I hope to give you a perspective on how machine learning and IoT actually intersect somewhat. So I always like to start by defining some of the terms that we're talking about, and Jack did a fantastic job of sort of laying the groundwork for us to talk about the different types of machine learning. And what he described were the different types of learning styles. And as I said, I'm going to be speaking about reinforcement learning. But before we get there, I also like to define machine learning and a couple related concepts, specifically neural networks and deep learning. Because I think that in circles outside of computer science, these terms are not well understood and are often conflated. So I like to show this Venn diagram where you have the set of all machine learning models or approaches, and I like to show that neural networks are actually one type of machine learning model that we can train and use to solve different types of problems. And deep learning is a subset of neural networks, specifically those that have many hidden layers. And so deep learning is a subset of machine learning, but not all machine learning models are deep learning models. In addition, but somewhat orthogonal to the distinction between the different types of machine learning models, are the different types of learning algorithms. So when Jack talked about supervised, unsupervised, and reinforcement learning techniques, those are techniques to train a model in order to perform a specific task. Models are essentially functions, but it's not like a linear function or an exponential function. It's a function that's a bit more complex that, for example, can take an image and output a classifier. It's an image of a dog, or it's an image of a cat. So these learning styles, supervised learning, unsupervised learning, and reinforcement learning can be applied to any kind of machine learning model, pretty much, regardless of whether they're deep learning models or others. So these are somewhat orthogonal concepts. So reinforcement learning, which again Jack described previously, is the type of learning that's a little bit more like learning how to do something versus learning that something is true. So as opposed to factual or propositional knowledge, reinforcement learning mimics the way that, for example, a human child would learn how to ride a bike, a bit through trial and error, through interacting with its environment, getting some feedback from how that interaction affected it, and then making some adjustment in order to achieve a well-articulated objective. Within the realm of medicine, there are a couple interesting applications of reinforcement learning, and I think that, to my mind, reinforcement learning is potentially the most promising and the most powerful type of machine learning algorithm that we're studying today. Within medicine, the task of creating an individualized or personalized medical treatment plan for a patient who has a specific disease is a wonderful application of reinforcement learning. You have the opportunity as a clinician to get feedback from the decisions you make in the ongoing care of a patient with a serious disease. And there are machine learning methods in order to optimize that type of personalized treatment plan. But machine learning can also be used for a broad number of other applications, and I think that one of the most interesting and somewhat surprising applications of machine learning is that you can actually use reinforcement learning to improve other machine learning models. So this has been applied, for example, in the analysis of somewhat noisy or fuzzy images like ultrasounds. The traditional segmentation techniques that are leveraged to discern the outline or the contour of images in ultrasound are difficult because the images are so noisy. So reinforcement learning can actually be used to train the parameters or hyperparameters of the deep learning network that is doing the image segmentation. So it's somewhat of a meta use of machine learning in order to improve the performance of other machine learning models. And that has a wide range of applications, but has been particularly effective within the analysis of noisy images. And because the title of this session was actually about deep learning and beyond, I wanted to point to an example that actually falls outside of medicine, but I think is related to some of the types of data sets that you have. So when we talk about machine learning and image analysis in particular, we're often talking about static images. But these techniques can also be applied to real-time video. And so the video I'm showing here is actually from some work that my company is doing with Daimler in the development of their autonomous driving capabilities. And the problem that's being solved is what's known as semantic segmentation, in which every single pixel of every frame of an HD video from a dashboard-mounted camera needs to be classified as belonging to either a pedestrian, the horizontal driving surface, a stationary object, etc. So this is an incredibly real-time, high-performance example of deep learning, and in particular reinforcement learning is used to train this model, to do pedestrian avoidance for autonomous driving cars. So you can imagine potentially doing something similar on video from surgical procedures, for example. Now I'd like to switch for the last few minutes of my time to talk about learning and IoT. So we've been told several times earlier today and also during yesterday's workshops that one of the underlying principles that has caused the renaissance of machine learning today is the huge exponential growth of data volumes. And that's absolutely true. Data volumes are doubling approximately every 2 years, which means it's growing at a compounded annual growth rate of about 80%. But in fact, most people, when they think about data, they think about that data living inside the data center or potentially in the public cloud. But it's a very different story. If you look at the growth of public cloud computing, for example, it's growing at about a 16% compounded annual growth rate, which means the vast majority of data that's being created and processed is not happening in a data center and is not happening in the public cloud, but is actually happening out in the real world. So, for example, an autonomous driving vehicle generates about 36 terabytes of data per day, one vehicle. That's nothing compared to the amount of data that's being generated by, for example, jet engines, which are projected, just the Pratt & Whitney jet engines will be generating about 2.5 zettabytes of data per year in the next year. So enormous amounts of data are being generated and processed on the edge, and I think that that's a less appreciated story. And there are implications in how we think about where to process data and the types of applications that we can support. And when I think about machine learning in particular, one of the premises is that you typically require a huge amount of data in order to, for example, train your model. And when that data is actually being generated by many different, for example, medical devices, you need to aggregate that data from those edge devices to a data center in which to train machine learning models. But then you need to deploy those machine learning models back to the edge in order to be able to act on real-time data as it's being generated. This is a little bit of a complex topic, but at my company we call it learn globally, act locally. So the idea is, and we're doing this work with Philips, for example, that has MRI machines that are smart and that come equipped with computing capacity. They're able to aggregate the data from all of the MRI machines that they have deployed globally to learn from the aggregate of those images to develop and train machine learning models that they can then deploy back to the MRI machines in order to do things like determine when the machines need to be recalibrated and also to aid in the diagnosis of diseases that are being studied by the people who examine the MRI output. Thank you very much for your attention. And
thanks. So my name is Christina Chen. I'm a nephrologist at Beth Israel Medical Center and also a research scientist at MIT. And today I'm going to be talking about gaining clinical insights from electronic medical records, specifically deciphering clinical notes. So this is a little different from the machine learning that you've been hearing in the rest of this session, but I think it's really important because this is where you can get additional information to put into your machine learning algorithms to build a more robust system. The database that I'm going to use to describe this today is the MIMIC3 database, which you guys heard about earlier from Leo, and many of you may have used it for your research projects in the past. This is a database based on information from Beth Israel Deaconess Medical Center, an academic hospital in Boston. It is over 46,000 patients that were admitted to all of our ICUs between the years of 2002 and 2012. And this is an open access database, so anyone can use it, including you guys. So in addition to the rich amount of structured data or discrete data that you can query with SQL, for example, like vitals and lab values and mortality, What I think makes this a very special database is that it has over 2 million free text notes. So this ranges from physician progress notes that happen daily to radiology notes. And this information is a little bit more difficult to get out than things like vitals and such in the structure data, but hopefully by the end of this presentation, I would have convinced you that there is just like a rich resource of information that you can gain by studying these notes. So first we're gonna go over a few examples of how using the notes has been used in literature, and then we're gonna go over like a very practical example about how you guys can go through and do this yourself. Okay, so acute respiratory distress syndrome. This is a severe inflammation of the lungs in critical illness, and it's associated with a high amount of morbidity and mortality. There's a group that wanted to study risk factors associated with this using the MIMIC database, but in order to do that, they had to diagnose their cohort to be able to get the group of people to study. And so to do this, they had to look at radiology notes. So this is an example of what our chest x-ray notes look like. And so the bolded section is the type of language that the people had to extract in order to be able to diagnose ARDS, or infiltrates in both lungs. If you guys wanted to use this to study, for example, pneumonias or fluid, these are the kind of notes you guys can look at. The next set of notes we're going to talk about are discharge summaries. So the antidepressants are very commonly prescribed, but some studies have shown that they're associated with increased risk of hemorrhage and strokes and mortality. So there's a group that wanted to go look at whether or not pre-admission use of antidepressants was associated with increased mortality. So the place you would get this from in our database are the discharge summaries, and this is just a section of the discharge summary. Citalopram is an antidepressant, so that's the kind of language that they would pick out. If you wanted to, for example, study other medications or classes of medications that you think would be harmful or protective, this is where you could look. And also the discharge summary also has all the past medical history, has a social history, and it has a summary of what happened in the entire hospitalization. So very helpful data set. And the next thing we'll look at is an example of how you can get information. So echocardiographies are ultrasounds that help you determine the structure and the function of a heart. I really like echoes because I find that in clinical practice, they're really helpful for helping you determine how you treat a patient, if they're volume overloaded, if they would benefit from medications to help their heart pump faster. And so there's over 45,000 echocardiography notes in the MIMIC database from before, during, and after the ICU course. So I wanted to make them in a format, convert them and translate them to a way that people could actually use them for research. Okay, so this is a heart. The first thing you want to think about when you translate this information into a usable format is how are you going to structure it? Like what exact information are you going to get from it? So as I mentioned, echoes help with the structure and function of the heart. So I decided that we're going to look at the chambers and the valves. So that's how I was going to describe my data. This is a sample echocardiography note, just so you get an idea of what it looks like, and we'll come back to this later. And so I'll show you an example of how I can get very discrete, interesting information that I could use from this. So let's take a snippet of the left ventricle. So the first thing we look at is mild symmetric left ventricular hypertrophy, which is the wall of the ventricle is mildly thickened. So that's one, mildly thickened. The cavity is normal, and there's severe left systolic dysfunction, which means that the left ventricle's pump is severely reduced. So if you enumerate it in this way from a numerical value versus text, it makes it easy to incorporate into your algorithms so that you could perhaps have a more complete picture of what's going on in the hospital. Okay, so now that we know what we want to get from it, how do we actually physically get this information? Well, there's a lot of tools out there. There's things like SNOMED, which many of you probably know. It's a collection of well-annotated terms that was used in the CTAKes that was mentioned earlier. There is the NLTK package, which is the natural language toolkit package associated with Python. There is CTICS mentioned before, that's created by Mayo. There's the NeurONER program, that is another graphical program that's produced by a recent graduate at MIT. And depending on your comfort level and perhaps what the data looks like, you can select something that works for you. So the first thing I looked at was, what does the language look like? If you remember what the chest x-rays looked like, they were very free-form sentences. We looked at the medications. They're very organized. This is somewhere in between. We see on the left side, there is the structure that I like to analyze. And then on the right side, there's a description of the structure. And it's nicely separated by colons. So initially, I was going to use the NLTK package to analyze it, but when I actually looked at all the discrete sentences in here, I saw that there was actually a really low number of unique sentences. And so that made things like regular expressions, which is a powerful searching tool, a much more simple way to look at everything. So what I did was I looked at, So I went through and I looked at the sentences. We categorized them into dictionaries to describe the different levels of severity, very similar to what we looked at for the left ventricle. And then I wrote a Python script, and we ran on the 46,000 echoes that we had to enumerate them. And then we released them with Mimic so that anyone who wants to use them can include it in their research. I have a particular interest in volume overload and acute kidney injury, and so we looked at a paper on that. There was a recent poster that was presented at the AHA that looked at progression of left ventricular dysfunction in septic patients. And then it was also used in a few of the groups in the Beijing Datathon that we recently went to. And so hopefully more people will find it useful in the future. Okay, so I hope that I've convinced you that the free text notes in Mimic and free text notes in general carry a large amount of information that could really, if used properly, make your research a lot more valuable and strong. And if you guys do end up using this database, it would be really great if you could consider donating the data or the annotations or the data back to our database so that we could share it with other people to improve the amount of data that we have and what can be used. Okay, thank you.
Good afternoon, I'm Mathieu Komorowski. I'm an intensive care physician. I work in the UK and in France. I'm also a PhD student at Imperial College. I'm affiliated to the Lab of Computational Physiology at MIT. I'm also affiliated with Harvard University, where I teach reinforcement learning in healthcare. So actually, for some of the preliminary work that I'm going to show you today, I was awarded last year the first prize here in machine learning for best abstract, I think, so I was kindly invited to join again this year. I'm really grateful. So reinforcement learning is very, very exciting, and I'm going to show you a very practical application of reinforcement learning without any buzzwords, really. It's really down-to-earth application. People have tried to use reinforcement learning in healthcare, and it's proven to be very difficult for different reasons. Of course, as always, you need a lot of data to train the models, but also validating the models that you have developed is extremely hard because you don't have a test bench. It's not like playing Atari or playing chess. Here we're dealing with human subjects, human beings. You cannot just work by trial and error. Sepsis is a big healthcare problem. We define it, for those who don't know, as a severe infection associated with organ failure. So if you simply have the flu, you don't have sepsis, right? Lots of people are affected by sepsis every year. Depending on how you look at it, infectious diseases could be the second or the third leading cause of death in the world. And people have reported that it could be the most expensive condition treated in hospitals. So clearly a huge problem that we need to tackle. Treating sepsis is complicated. Basically, the treatment evolves around three big axes. You need to deal with the source of infection. You need to give antibiotics. You need to remove abscesses if the patient has any. The second aspect, and that's really the pain point, is correcting hypovolemia and vasoplegia. So the patients with sepsis have hypovolemia. They have a reduced circulating blood volume. They have fluid loss. They are dehydrated. but also there are blood vessels for some of the patients, the most severe, the blood vessels become loose, they have vasoplegia, and they may require vasopressors, so drugs to squeeze those vessels to restore basically an appropriate volume of blood vessels, and then you need to fill them as well with intravenous fluids that you give from in the vein. And the third aspect is about treating secondary complications when they occur, so acute kidney injury, clotting disorders, and so on. And more or less, this we have an idea on how to do it. Reinforcement learning, we've heard all about this, so I'm going to go quickly. Crystal gave a really great explanation on the principle behind reinforcement learning. I'll give you a very simple explanation. Here is, if you consider a grid world, a simple maze like this could be the states of a reinforcement learning framework. The agent in my algorithm, in my example here, is the rat, and the objective of the rat is to reach the cheese as often as possible. I'm French, so it's all about cheese, and needs to avoid being electrocuted as often as possible. So the goal of the reinforcement learning agent in this example is to find a policy, to find what are the best decisions to be made in every state of the system in order to reach reward as often as possible, and in order to avoid the penalty of being electrocuted. Okay? So we can formulate, now keep this in mind, we can formulate medical decision as a reinforcement learning problem. Here in medicine, we deal with a physician, so the physician is the agent. The patient is the environment, okay? The physician acts on the patient by prescribing drugs or intervening or taking the patient to surgery. But in my example, it's about giving intravenous fluids and vasopressors to a patient with sepsis. The patient's going to respond to those actions, to those prescriptions by switching states, going into a different clinical state, maybe better, maybe worse. If the new state is better, the physician's going to be rewarded. The behavior that led to this new transition is going to be reinforced. This is why it's called reinforcement learning. Positive behaviors are reinforced. So if we have a framework like this, we can ask two questions. How good is the policy of a physician? What is the value of actions taken by actual doctors? And then can we identify an optimal policy? Of course. Can we improve the decisions that are made by doctors? Can we find better decisions? And if we go back to the grid world, it's very straightforward. This time it's a patient, and the objective of the agent is to send the patient home as often as possible rather than sending the patient to the cemetery. So about finding the right actions in every state of the system, what is the most optimal dose of drugs? It's as simple as that. And you see that this is agnostic of the type of problem that we would want to address. It would work as long as you have the data, as long as you're able to model a disease process, you can use reinforcement learning for pretty much anything in medicine. So I use two data sets in my research, Mimic, of course, and for model development, and then the Philips data set through a collaboration with Philips Healthcare. So we use the EICU database. Altogether, this is about 100,000 patients from well over 100 hospitals in the US. Adult patients with sepsis were included, and I'm going to skip on the technical details, but it's a very high dimensional data set that we used. So again, we developed the model on Mimic. We learned an optimal policy, we learned an optimal treatment strategy for sepsis, and then this was tested on the Philips data. And these are some of the results. So we can compare the two policies, the policy of doctors, the treatment strategy of doctors here on your left, and the treatment strategy that maybe would be optimal according to the estimation, according to the model here on the right. And so what you're looking at is the distribution of doses according to doctors on the left for vasopressors and intravenous fluids. Okay? What you see is that most often doctors, they don't give a lot of vasopressors, about 10-15% of patients are on vasopressors, but they tend to give a lot of intravenous fluids. Does that make sense? Can you follow the slide? So it's showing you the distribution of actions for the two drugs. And if you look at the optimal policy, it looks quite different. Maybe more patients should be on vasopressors, about 70% of them. Probably on a low dose of vasopressors would be appropriate, and this is quite interesting from a clinical standpoint. And the doses of intravenous fluids should probably be lower than what we're actually doing. And this is quite interesting when you look at the literature. More and more evidence is coming in that maybe we give too much fluid to our patients with sepsis, and again, treating vasoplegia with vasopressors would make a lot of sense because it's a key feature, it's a key physiological feature of patients with sepsis. So from a clinical standpoint, this is not completely absurd, the kind of results that we get. Are the suggested doses optimal? How do we know? It's all retrospective. It's a very difficult question. So because we don't know the outcome of an action that was not taken in the past. Okay? So what we did is I looked at the difference between the dose given and the dose recommended. If this difference is 0, it means that the patients in the past received the optimal dose, the suggested dose. And this is the central bin you see here in the two plots. So where the black arrow is, the central bin is where the patients received the suggested dose, and you see that the mortality, so it's in blue and red, the mortality is the lowest for this dose bin. And the further away you go from this central bin, the more the patients died. So this is maybe an indication that the suggested doses were indeed optimal. We can try to predict the mortality with optimal actions. I'm going to skip the details, but the estimate we have, again, it's an estimate, is that the mortality could potentially go from 18% in the cohort to about 10%. So even if we achieve only a fraction of this reduction, this would mean tens of thousands of lives spared throughout the world, potentially a huge impact. And last slide, I'm going to be on time. Everything I said so far is just a black box. A key challenge in machine learning is to understand what the policy is doing, what's happening under the hood. And this is one attempt at doing this. We can, for example, improve the interpretability of the policies by looking at the relative importance of each features in the model. What parameters are the most important when making a decision of giving a drug? So this is the two plots on the right is about the vasopressors, and what you see is that the parameters at the top that are most important when the doctors decide to give vasopressors or when the optimal policy suggests to give vasopressors, the parameters at the top are very clinically meaningful. Blood pressure, arterial lactate, and so on. So maybe the model is suggesting something that is actually clinically interesting and relevant. And I just want to be as close as possible to the final time. That's the end. Thank you very much.
Thank you so much, the panelists. There's a few questions that have come in through the poll. So why don't we start there? I think the first question that I want to ask is actually to David. I think there was a question about whether there's any clinical decision support that was built into your clinic. And then I actually want to add a follow-up to this, which is, I think Matthew repeatedly mentioned that his work right now is retrospective. What would he have to do to get you comfortable for you to try that in your patients?
Thanks. So two good questions. I'll take the first one first. So what clinical decision support is built into our clinic? So let me give one concrete example where we are using machine learning, not for necessarily for clinical decision support, although I would say it is useful for supporting decisions. Let's talk about a specific problem. Obesity, huge problem. How do we identify obesity today? We use body mass index, a simple ratio of height to weight. But we know that body mass index can be incredibly misleading in patients that are short, very tall, and it really doesn't do a good job of telling us what a healthy amount of body fat mass is. So there are other methods that have been developed, including body composition testing. But what we're looking at is how we can use just somebody's body surface data to predict or infer their body mass index. And so we're using thousands of data points from our 3D body surface scan, feeding those data points into a statistical learning, machine learning model, which we've trained on thousands of patients who also have DEXA bone densitometry scanning, which is the objective gold standard for assessing body fat mass. So in this way, we're able to non-invasively predict somebody's body fat mass using a tool that could easily be deployed in any clinic or perhaps even mobily as well. and getting at your question, so now how do we integrate that into clinical decision support? What we're doing is very ad hoc right now. We have a very high-touch patient experience where we learn from our patients what problems they have and how we can better serve those problems with data. So what we're going to be looking to do over time is increasingly automate the decisions that we make with our patients, but it has to start with first collecting the right data, which frankly we don't do when it comes to health in the traditional healthcare system. To your second question about retrospective versus prospective data, as a bioinformatician, retrospective analysis of electronic health record data is really near and dear to my heart, and I think that's a great way to develop hypotheses, but ultimately we do need to explore and test those hypotheses prospectively. At the end of the day, observational data is observational data, and I don't think, even large amounts of data, I don't think we're going to circumvent that problem.
Thanks, and I would love to hear actually the other panelists' view on this as well. There's been a big debate right now. Actually, I think there's a question here about Matthew, whether your data is published. There's a big debate actually both in the academic journals as well as in the clinician community about where the bar should be for machine learning, whether we need prospective data before we can publish or before we can act on it. So given the clinicians here, as well as I think Christo's experience in cars, where we clearly do something very different, I'd love to hear your perspective on this.
So, can you reframe the question a little bit when it outside of the sepsis realm?
Sure. So in cars or in consumers, actually in autonomous driving, where you can clearly say the bar for safety is actually quite high, there's actually relatively little getting published, and there is a lot of testing that is already happening in the real world. So I'm very curious to hear your perspective on how you think the community came to that conclusion. And then what you think should be applied in healthcare. I'm very also interested in what the clinicians think should be happening in healthcare.
So one of the tenets of machine learning is that we have a difficult time proving optimality of any of these approaches. It's difficult to prove why a machine learning model works or doesn't work. A lot of the research is done through trial and error. It's very similar to how reinforcement learning works. We try models and observe how they perform in real world situations, and then we as humans determine what a good model is to perform a specific task. And we typically use some kind of criterion that says a machine learning model is good if it can repeatedly simulate the way that a human expert would make decisions in that realm. So for autonomous driving, the level of confidence that we have in these machines will likely be whether the vehicles avoid collisions with better accuracy than human drivers. So if human drivers are in more accidents than cars, then we will believe that that's a good system. We hold the similar standards for example, autopilots on airplanes. And so, so I think that probably addresses the question. I don't know if you want to comment.
I mean, in the particular case of healthcare, there is a whole group of algorithms and people actually working on what they call safe reinforcement learning. So the idea is that we already have an existing policy represented by what the doctors do, and the idea is to deviate only slightly from this and try to have algorithms that can guarantee that the new policy is hopefully only going to perform better by taking baby steps basically towards what is an estimated more optimal solution, and while assessing constantly along the way. It's obviously a very critical question. We cannot function by trial and error. We don't have a test bed for human beings.
So ideally in medicine, we would prefer to have randomized controlled trials, but we really can't for this population. We can't be like, for this septic patient, we are going to give them a lot of fluids and no pressors and things. And so I think that with this data, it helps direct us to perhaps more optimal ways of performing without the ethical concerns of a randomized controlled trial. A lot of times in practice, there's a wide variation in the way that clinicians actually practice, and there's maybe not that much data to support every action that they make. And so I think that by following this, we can get more data and see how things are in the future. And if we never act on any of this and we never use this, then I think it'd be difficult to get additional other information.
I'm finding the questions that are currently being asked very interesting. I think I just mentioned that there's a big debate right now in the community about how do you even publish on reinforcement learning in healthcare. Matthew, I don't know, is your data currently published?
So the data is not published. I mean, so it's derived from Mimic. The code is online. I'm happy to direct you to my GitHub account if you want. The Philips data, some of it is publicly available, not the full data set that we used, but the value, so probably the most valuable aspect of the project is the data and the fact that I spent probably several years tidying this data set.
And is your research now published as well?
We have some preliminary papers out, not the big results, no, not yet.
I think what's really interesting to me right now is many of the questions that I see being asked is very similar to many of the objections that are coming from when I do NIH review panels or when I do paper reviews. Many of them are around, I think, many physicians still being quite uncomfortable with machine learning generally, especially with reinforcement learning. I think reinforcement learning is now doing some very interesting things in places where the policy is very clear and where the rules are very well defined. So things like chest, Go, we are clearly showing that in fact you don't even need many moves. You don't need to train for a very long time before you get very good results. I feel like as a community we have to figure out a way to really trial some of these reinforcement learning deep learning things in the healthcare environment themselves. I think Matthew mentioned, I think a number of folks alluded to the fact that we have spent many, many years now trying to figure out how do you do this in different spaces where it's safe. And I think unless we really start to test some of these things, it's very hard for the field to really advance. And just like Matthew, I just want to run down the clock. Thanks, guys.